I'm Gagan, and I want to talk about the critical barrier standing between researchers and new medical treatments. Currently, the scientific community relies heavily on zebrafish to study hemostasis, the process of blood clotting. This isn't just basic science. This is the first step in discovering drugs for hemophilia, von Willebrand disease, and deep vein thrombosis. The problem is the data bottleneck. Right now, after researchers perform a bleeding assay, they are forced to manually trace blood spots using a computer mouse. This is subjective and prone to human error and incredibly slow. But here's why it even matters. Those measurements are the deciding factor in whether a potential life-saving drug proceeds to clinical trials or gets thrown in the trash. If the manual measurement is wrong, we might discard a drug that actually works or waste millions developing one that doesn't. By relying on manual labor, we are essentially stalling the discovery pipeline. We need a system that offers standardization, ensuring that a measurement taken in a lab in Texas is consistent with the one taken in Tokyo. This is the only way to make data truly viable for pharmaceutical development.
Thanks, Gagan. I'm Devon. To solve this issue, we didn't just build a theoretical model. We built a tool for immediate laboratory integration. We're proud to announce that we've already begun the process of incorporating this innovation for hemostasis research at Dr. Perdue Jagadishwaran's laboratory at the University of North Texas. And the direct impact of that collaboration is by automating the outlining process, we provide researchers with immediate quantitative and phenotypic data. Once our tool generates the metrics, researchers can map specific genes to clotting functions to identify novel gene targets for diseases like hemophilia and deep vein thrombosis. But the impact goes beyond just speed. It's about ethical science. Our project directly supports the three R's of animal research, specifically reduction. Because our computer vision model eliminates human error and inter-observer variability, our data is cleaner. This means that labs can achieve statistical significance using fewer animals, reducing the overall number of zebrafish needed for drug trials. Essentially, our tool is the engine for high throughput screening. Instead of spending days on one mutation, the lab can analyze hundreds in parallel. We're effectively removing the manual labor from the scientific method, allowing researchers to focus on the results, interpreting the biology to develop life-saving therapies.
Hi, I'm Rohan. Before I present the actual model, I want to show you what it's like to manually trace the zebrafish on your computer. Most researchers nowadays will take images of their zebrafish and upload them to common imaging software like ImageJ. The problem with these imaging softwares is that they're web application based, meaning you can't use devices like your iPhone or your iPad as tracing devices. In order to illustrate the difficulty of manually tracing, I have a computer mouse and a mousepad here, and I'm going to try to trace this as accurately and efficiently as I can. So I'm just going to do a fast and precise outline around the fin. And you can notice automatically that it's not too good. And I am trying as hard as I can. I'm not doing anything. And if we zoom in, we can see these padding inconsistencies in the outline that don't accurately fit the actual edges of the zebrafish. This is a crucial mistake because, like Guggen said, it can be the reason why companies waste time or discard useful or non-needed drugs. And as a solution, we developed Zebrafish Hemostasis Mapper, a more efficient and consistent solution. Now I'm going to show you the actual model. First, you click the upload area, then you choose whatever image you want. In this case, it's the same as the physical sketch I showed you earlier. It pops up here, you click trace area, and you get your precise fitted outline around the zebrafish. But there's more that goes on behind the scenes. What happens first is when you click this button, it stores the image into the model's memory. One of the key properties about zebrafish is that they're a lot darker than the petri dishes that researchers use to store the zebrafish. And because of this, we can convert it into an HSV color space. A color space where we can exploit things like the brightness, saturation, and contrast of the pixels in order to find objects that we want to outline, like this zebrafish. Then a mask is created, which basically filters out pixels which have lower values than the mask's values. And we get this kind of semi-blob of whatever zebrafish there is. And then, as a polish, we extract contours, which are shapes that represent detected objects. And after this, we put everything together and we get this accurate, beautiful, precise outline of the zebrafish. But the preciseness isn't the only thing that makes this innovation so valuable. It's the accessibility. Because this is a software-based application that is deployed on a web interface, it requires no hardware expenses for labs, and it can be deployed by any researcher or company globally. We took one of the biggest problems with zebrafish hemostasis research and made it a 2 to 10 second task, saving loads of time for any researcher or company around the world.